This road should make every ordinary wheel bounce, but one very strange shape can cross it while its axle stays perfectly level. The road is already fixed, so what shape must the wheel be? That question sounds backward. We usually choose a wheel first and build the road beneath it. Today, we will start with the road, let the equations draw the wheel, and test whether the result can actually roll. A circle is the first obvious guess. On a flat surface, its center never changes height. On this triangular road, the same circle climbs every peak and falls into every valley. The axle records every mistake. A smooth ride needs two things at the contact point. The axle must remain on one horizontal line, and at the exact instant of contact, the point on the wheel must be stationary relative to the road. That is rolling without slipping. This is why a square wheel is not impossible. Give it a road made from matching inverted catenaries, and each corner hands the motion to the next side while the axle remains level. A strange wheel simply demands the right road. Now reverse the problem. Keep this jagged road, place the axle on the blue line, and ask the road to reveal the rim one contact point at a time. Every point we need is already hidden in the road's height. Call the road height y because the axle sits at height 0. The distance down to the contact point is just negative y. That distance becomes the wheel's radius at this instant. The first equation is almost embarrassingly simple. The second equation controls rotation. If the axle moves by a tiny distance dx, the wheel must rotate just enough to cancel that motion at the contact point. No slipping gives d theta over dx equals 1 over y. Now the construction becomes visual. Move along the road. Measure its depth. Rotate that vertical contact vector back into the wheel's own frame. The tip leaves a trace, and that trace is the only rim that can roll on this road. At first, the answer looks spectacular. It has petals, spirals, and a center full of crossings. It even rolls for a while. But it is not a usable wheel because after several road periods the trace misses the point where it began. The failure is not numerical noise. During one road period, the wheel turns through a specific angle. Repeat the road, and the next copy of the rim is rotated by that same angle. If those rotations never complete a full turn, the rim never closes. For 5 identical petals, one road period must rotate the wheel by exactly 1/5 of a turn, 72 degrees. In symbols, the integral of 1 over y across a period must equal negative 2 pi over 5. We cannot change the road's zigzag pattern, but we can move it slightly farther from the axle. That changes every radius and every tiny rotation. Watch the endpoint. The tangled curve loosens, the gap shrinks, and the turn approaches 72 degrees. At a depth of 3.287136, the final point lands on the first. 5 road periods make one complete revolution. The open trace becomes a single closed wheel. Now test it. The contact point moves along the triangular road while the wheel rotates around the fixed-height axle. The rim changes radius before every corner, so the center never needs to climb. The bounce meter stays flat. This shape is not decorative. Each curved side is a piece of a logarithmic spiral produced by the straight slope beneath it. The 5 sharp joins remember the 5 peaks of the road. Every feature has a mechanical reason. The same idea creates entire families of pairs. A square finds a catenary road. A focus-centered ellipse finds a cosine road. And this 5-petal wheel finds our triangular road. Wheel and road are 2 halves of one motion. Even the number of petals is not forced. Keep the same triangular pattern and change only its distance from the axle. A larger turn per period closes after 3 copies. A smaller turn closes after 4, 5, or 6. One road pattern hides an entire family of wheels. The geometry also does not care how quickly the wheel travels. Run the same construction slowly, then 4 times faster. The contact point changes speed, but the no-slip relation is unchanged, and both axles trace the same perfectly horizontal line. There is one practical warning. Our triangular road has sharp corners, so the exact wheel has sharp joins too. Real materials would hate those points. Round the road slightly, apply the same equations again, and the wheel rounds with it while preserving the smooth ride. Finally, audit the simulation instead of trusting the picture. Across a full revolution, the reconstructed axle remains level to floating point precision. The no-slip step residual is effectively 0, and the final rim point returns to within 2/millionths of the first. That is the deeper idea. A shape is not perfect by itself. Perfection describes a relationship between the shape and the world around it. On the wrong road, this wheel is absurd. On its own road, a circle is the imperfect one. So the perfect wheel is not always round. It is the shape that makes its environment feel flat. Which impossible road should we solve next? A sine wave, a staircase, or a fractal edge?